Right. Consider this situation, all of you. There is liquid filled up to a certain height in a container. Okay. Assume the liquid's density is rho. Container is not accelerated. Okay. So it's a non-accelerated fluid. Okay. You can see that the liquid is open to the atmosphere. One of you quickly tell me how much is the pressure here at the upper surface of the liquid?
P naught, sir.
P naught, atmospheric pressure. Yeah, correct. Fine. Then anywhere inside the liquid, as you move deeper, the pressure will increase. Okay. Now, one of you, from your everyday experience, you tell me if we make a hole here, what do you expect to happen? Does the liquid flow out or air flow in? Outside there is air. Okay. Inside the container, there is liquid. What will happen if you make a hole there?
So the liquid will flow out.
Liquid will flow out. Now, see, liquid is something which can flow. Air is also something which can flow. Both liquids and gases are fluids. Why is it that the liquid goes out? Why does the air not go in? Air also has a way to enter inside, no? Why do you think only liquid going out happens? I'll give you all a minute. Think about it. Any answer, anyone? If we make a hole there, why is it that the liquid flows out? Why not, or why does the air not flow in? Okay. See, fluid, whether it is liquid or gas, tends to flow from a region of high pressure to a region of low pressure. Now, visualize the situation here. Now, we are going to make a hole at this level. Fine. One of you quickly tell me what is the pressure of air outside the hole? How much is the pressure here?
Not, sir.
P naught, atmospheric pressure. Okay. Air being a gas, its pressure does not vary significantly for such small height. Okay. So pressure here will be P naught, pressure here also will be P naught, here also it will be P naught itself. On this side, it will be P naught everywhere. Okay. For small heights, atmospheric pressure doesn't vary significantly. Okay. As you go to very large heights above the surface of Earth, atmospheric pressure does vary significantly. But for small heights like the height of a container, you can ignore that variation. So air outside the container is at a pressure P naught. Next, one of you tell me, can you comment on the pressure of liquid inside the hole? Okay, just inside the container near the hole. I don't want the exact value. Just tell me whether it will be equal to P naught, greater than P naught, or less than P naught. Since the point is at a certain depth from the free surface, it will be at a pressure greater than P naught. So the liquid inside the container at that place is at a higher pressure than the air outside the container. Now, if you make a hole here, okay, fluid tends to flow from high pressure to low pressure. Liquid is at higher pressure. The inner side is at higher pressure. Outer side is at lower pressure. So you will see fluid moving from inside to outside. That is why you will see liquid flowing out from here. You don't see air going in. Okay. Is this clear to all of you? Any doubt in this? If you ever have to comment on the direction of motion of a fluid, you first think about the pressure on one side and on the other side. Then you will be able to tell which way it will go. Okay. Let's consider another situation now. You all must have observed this. Just a moment. Let me download one diagram or a picture. Okay. I'm sure you all must have seen water stored like this or supplied like this. Now, when you open the tap and start filling water in a water bottle or something, now you open the tap, water flows out. It makes sense. Pressure of water inside the tap may be more than pressure of air outside, so water flows out. That's reasonable. Okay. But from your observation, you tell me if you have, I'm sure you all must have used such water bubbles. So as you are filling the container with water from this, okay, from this system, do you only observe water flowing out, or do you also observe air going in? Do you see bubbles forming inside or not as you drain water from it? From your experience, you all tell me. How many of you have used containers like this? None of you have ever filled water from a container like
So
this?
we have, sir.
So Yusuf, did you observe anything? Like you open the tap and start filling the water bottle. Do you only see water flowing out, or do you ever see bubbles forming inside that can?
Sir, bubbles form inside the can, on the top can, one into.
Obviously. Okay, bubbles form, right? So air must be entering in. Is that correct or not? Huh. So in this kind of system, when you open the tap, water starts flowing out. But after some time, after a short while itself, okay, even before you fill the water bottle, you will see bubbles forming inside. Means air is entering inside from the tap. There is no other space from which air can enter inside. From the tap itself, it will enter. Why is that happening? Water flowing out is reasonable. The water just inside the tap, I mean, at the water at this level, may be at a pressure greater than P naught. That is why it is flowing out. Okay. But after a short while, why does air enter inside? Why does that have to happen? Think about it. I'll give you all 2 minutes. Think carefully. You have to explain why air enters into the tap. Why don't we just observe water to be flowing out? Okay. Right. Yusuf, your answer is almost correct. Okay. So understand carefully what happens in this system as you drain water from it. Initially, let's assume water is filled up to this level. Okay. When you just place the can there, you see the water settling at this level. Obviously, there will be water in the lower can as well. Fine. Now, when you just arrange this system, okay, the pressure here will be equal to P naught. Okay. So see, basically what you do, you bring the can and you invert it and place it on top, right? So there is some air present inside it, and that air, let's assume it is at atmospheric pressure. Okay. Outside also the air is at atmospheric pressure. Fine. Now, initially, okay, when the water is up to this level, let's call this level as L1, initial level. When the water is up to that level, the air that is trapped inside that bubble, it's at a pressure P naught. And as you go down in the container, the pressure increases. So the pressure here, okay, pressure of water close to the tap will be significantly greater than P naught. So when you open the tap, you will see water flowing out of the tap because outside there is air at pressure P naught. Inside there is water at a pressure greater than P naught. Fine. Now, as water drains out of this container, okay, let me copy the entire diagram. As water drains out of this container, one of you tell me what should happen to the empty space at the top? Should that volume increase or decrease as water drains out?
Increase.
Obviously. Okay. Water level will be coming down. So you'll see something like this happening, right? From the level L1, let's say water has decreased or fallen to a level L2. Fine. Now we have to comment on, or we have to think about why air enters into this bubble or this can. Why don't we simply see water flowing out? The air trapped here was initially at a pressure P naught. Now what is happening? That air is expanding. Okay. When air expands or when a gas expands at constant temperature, the temperature will be room temperature itself almost. When volume increases at constant temperature, pressure decreases. Okay. Some of you may have studied this in chemistry. It's called Boyle's law. P1 V1 equal to P2 V2 if temperature is constant. You will study this in physics also in thermodynamics. Okay. So at constant temperature, if a gas expands, if the volume of a gas increases, pressure has to decrease. Okay. So as the water level in the can decreases, the pressure of air here decreases. It becomes less than P naught. Fine. Now this height, let's call it as Y, which is a variable. Then the pressure of water just inside the tap, let's call it P. How do you write an expression for P? Pressure at the top plus rho g y. Okay. Now pressure at the top initially was P naught plus the height initially, let's say, was capital H. So the pressure at the bottom initially is P naught plus rho g capital H. Now as you drain water out of that can, what is happening? Pressure at the top is decreasing. This happens because volume of the air is increasing. Okay, the gas is expanding, pressure has to decrease. And the Y value, the height is also decreasing. So both these values are decreasing. Then there is a chance that pressure at the bottom, okay, pressure of water near the, what do you call, tap, becomes less than atmospheric pressure. It won't immediately become, but after you drain out a certain volume of water, okay, the pressure near the tap, pressure of water inside the tap becomes less than atmospheric pressure. Then you will see an air bubble going inside. Okay. When an air bubble goes inside, what will happen? When air enters inside, what will happen? The pressure here will again increase. Some extra air molecules will come and fill that space. Okay. If the existing air expands, pressure decreases. But if you pump in more air, then pressure can again increase. Okay. Then this pressure increases. And if this pressure increases, this value will increase. And on the whole, the pressure inside the tap becomes more than P naught. Water will again start flowing out. And till when will it again flow out? Till the pressure inside again becomes less than P naught. Okay, and that cycle will keep on repeating. For some time water will flow out, then an air bubble will go in. For some time water will flow out, then an air bubble will go in. That cycle will keep repeating till all the water is drained out. Okay, is this clear to all of you? Any doubts in this? Okay. Okay. Next, consider a situation like this. Just a moment. Suppose there is a long tube filled with a liquid. Now you can, like, the tube is open at the upper end. So you can tell the pressure at any depth if you know the density. Depth and density, if you know, you can tell the pressure. So suppose this is filled with water. Okay, take this as a problem. Density of water, you know, it is 10 power 3 kg per meter cube. Okay. I want you all to find out how high a water column is needed. Okay, how much height of a water column is needed such that, see, the open end, the pressure is atmospheric pressure, you all know that, and as you go deeper, the pressure increases. Okay, atmospheric pressure also approximately take it as 10 power 5 pascals. Pascal is the SI unit of pressure. I want you to find out the height of the water column for which the pressure at the bottom becomes twice the atmospheric pressure. Okay, do this all of you. I'll give you all 1 minute. Shouldn't take longer than that. Vanilla Aishwarya, the answers you have given are correct. Very simple. You know the pressure here, and pressure at a depth is pressure at the upper surface plus rho g multiplied with the depth. That's all. You substitute the given density and atmospheric pressure in this, you will get the height as 10 meters. Okay. What does this mean? In a non-accelerated container, okay, you will need water column. You will need a water column of height 10 meters. Okay. 10 meters is a significant height. Comparing it to the height of buildings, usually each floor of a building is about 10 feet. Okay, so 3 point something meters. So if you want 10 meters, it's about ground floor, first floor, second floor. So imagine a building which has 2 floors, it is that long. So you need a water column of that much length, 10 meters, to add a pressure of 1 atmosphere. Okay, to increase the pressure by 1 atmosphere, you will need that length of a water column. Now here, the upper surface was open to atmosphere. Okay, so the pressure at the upper surface is already P naught. Another 10 meters of water column will increase the pressure by another P naught, and final pressure becomes 2 P naught. Okay. Same situation had the upper surface been closed. Okay, had the tube been closed at the top. Okay, imagine something like this. Just a moment. Suppose it's a closed tube. Okay, if you want, you can imagine the lower end to be open, or it may be closed also. It's your choice. Now, if it's a closed tube, the upper end is not open to atmosphere. The upper surface of water is not open to atmosphere. Okay, so there is nothing striking water from above. So the pressure here will be 0 this time. Okay, then if you take a water column of height 10 meters, you will see that the pressure here at the bottom end becomes atmospheric pressure. Basically, P is equal to, or pressure there is equal to, pressure at the upper surface, which is 0, plus density of water multiplied with gravity, acceleration due to gravity multiplied with the height. So that is 10 power 5 pascals, which is 1 atmosphere. So you will need a water column of 10-meter length. Okay, a vertical water column of 10-meter length to create a pressure of 1 atmosphere. Okay. Now, usually, see, water, it evaporates very easily. Okay, even at room temperature, it can evaporate very easily. Consider mercury. The density of mercury is 13.6 gram per cc. That is 13,600 kg per meter cube. 1 meter cube of mercury will weigh this much. Okay, or will have this much mass. You can also say it is 13.6 times that of water. 13.6 times the density of water. It's very dense. Okay, and mercury doesn't evaporate at room temperature. So if you have a certain volume of mercury, even if you expose it to atmosphere, you won't see the volume of mercury changing. Okay, you won't see the molecules disappearing or evaporating. Fine. So usually to measure atmospheric pressure and all, they make use of mercury columns. Okay, vertical mercury columns. Now consider a mercury column instead of a water column. Okay, just a moment, I'll show you the diagram. Consider a mercury column which is closed at the top. Okay, if it is closed at the top, the pressure here will be 0. Okay, I want you to find out the length of this mercury column, okay, or the height of this mercury column, such that the pressure at the bottom of this column becomes atmospheric pressure. Atmospheric pressure means 10 power 5 pascals. So how much is the length of the mercury column? You can use a calculator if you want. Do this quickly and tell me the answer. Right. If you consider this pressure as 10 power 5 pascals, which is close to atmospheric pressure, not the exact atmospheric pressure, to create this much pressure, you will need a liquid column of, or a mercury column of rho g L. Now, density of mercury is 13,600. We'll use SI units only. Acceleration due to gravity is 10, multiplied with the length of the mercury column. Send 13,600 and 10 to the other side, you will get the length as approximately 0.74 meters. Okay, if you take actual atmospheric pressure value, okay, if you take the pressure to be exactly equal to P naught, then the length of mercury column required will be close to 0.76 meters. Okay, that is 76 centimeters of mercury will be needed. Okay, that means a 76 centimeter long column of mercury, vertical column of mercury will be needed to create a pressure equal to atmospheric pressure under the influence of gravity, of course. Okay, that is why atmospheric pressure is sometimes expressed in terms of length of the mercury column. Okay, so pressures can be expressed as lengths of liquid columns. So you can say one atmospheric pressure, okay, that is 1 atm, which is basically P naught, is equal to 76 centimeters of mercury. 76 centimeters is a length. Why are we using length to indicate pressure? It means you use a mercury column which is that long, vertical mercury column which is that long, you can create a pressure equal to 1 atmospheric pressure. Okay. The same can also be created by using a 10-meter long column of water also. Okay, we had derived this in the previous problem. Okay. So to create a pressure equal to 1 atmospheric pressure, you will need a very long column of water. I told you this will be about 3 floors long. But 76 centimeters, this is less than 1 meter. You can easily arrange this in a lab. So this is another reason why we use mercury to measure atmospheric pressure at a certain region. Okay. Now, how exactly is atmospheric pressure measured? The instrument used to measure atmospheric pressure is called a barometer. Consider a situation like this. Let's assume there's a liquid container first. Just a moment. Okay. Consider some random liquid in a container. And then let's say a tube is immersed into this liquid. Okay. Narrow tube, completely immersed into this liquid. The tube is open at both ends. Okay. Think of it as a glass tube. Okay. You can see the liquid inside the tube. Right. Now, since the tube is open at both ends, the pressure here at this depth in the liquid will be equal to the pressure here inside the tube. And the pressure here at this depth in the liquid will be equal to pressure here inside the tube. That's fine. Okay. Imagine closing this tube at the top. Okay, like you put your hand inside and close the tube. If you want to try this, don't try it with mercury. Okay, mercury is carcinogenic, it causes cancer. You are not supposed to allow mercury to touch your skin directly. You can try it with water if you want. Okay, and I'm sure most of you would have tried it already while drinking water using a straw or something. Now, so what I'm asking you to do, imagine doing is close the top of this tube. Okay, you can close it with your thumb or you can seal it using something else also. The lower end is still open. Okay, let me make it clearly visible that it is open, the lower end. Fine. Okay, it's like this. Lower end is open. Now imagine pulling this tube or gently lifting this tube out of the liquid. Can any of you tell me what you will observe as you bring this tube out of the liquid? The lower end is open. Okay, but we have sealed the upper end and we are pulling the tube out. Can any of you tell what happens based on your experience? Or you can predict also. Okay, I got one answer as it pulls itself down. Okay, so you are saying the tube will be heavy, so the tube. Okay, I want you to you are pulling the tube out. Okay, of course the tube will feel heavy. You'll be experiencing the weight of the tube. That's fine. What happens to liquid level inside the tube is what I'm asking. The tube is definitely being pulled out. What happens to liquid level inside the tube? Pawan, what do you think? If you can answer, otherwise, that's fine. Aishwarya, what do you think will happen?
So the level will remain the same.
Okay, so you are saying as you pull the tube out, you will observe something like this. This is what you're saying.
Yes, sir.
Okay. Why is the liquid rising up? I mean, why is the liquid level inside the tube higher than the liquid level outside? How is it getting supported? Okay, let me explain. See, due to gravity, the liquid will have a tendency to go down. Okay, the weight of the liquid will be pulling it down. But the pressure here is atmospheric pressure. If the pressure here is atmospheric pressure, then the pressure here at this level inside the tube will also be atmospheric pressure. Why? Because there is a continuous fluid between those 2 points, right? All the way from here to here, there is a continuous fluid without any break in between. So as you go down in the liquid, pressure increases. As you go up, pressure decreases. So from here to here, you will see pressure increasing. But again, as you go up inside the tube, the pressure decreases back to P naught at the same level. Okay. If the pressure at that level in the tube is P naught, then the pressure at the top of the tube here will be less than P naught. Why? It's not exposed to atmosphere, first thing. So air molecules won't be striking it. And if the pressure here is P naught, depending on the height by which you take it out of the container, the pressure there at the top can be expressed as P naught minus rho GH. Because when you go deeper in a liquid, pressure increases. Then when you go higher in a liquid, pressure has to decrease. Right? That surface is not exposed to the atmosphere. So if you want to calculate the pressure there, you will have to do it this way. So as you slowly lift the tube out of the liquid, the pressure inside the tube at a level equal to the level of liquid outside will be P naught. Pressure anywhere above that will be less than P naught. Okay. So how much is the exact pressure at the top depends on the height by which you lift it up. Okay. Now, for small heights, P naught minus rho GH will still be positive. Okay. Rho GH won't be enough to balance P naught. It will be positive. There is positive pressure in the liquid there. What does that mean? It will be pushing that cap or lid or your thumb. Okay. Liquid will be pushing it. It's under some pressure. Fine. As you continue lifting the tube out, as you continue pulling the tube out, that pressure will keep on decreasing. At one moment or at some height, the pressure at the top, which is P naught minus rho GH, will become zero. Definitely, as you keep pulling the tube out, we are making an assumption here. We are assuming the tube is long enough. Okay. So suppose the tube is long enough, as you keep pulling it out at some height h, okay, let's call it h naught, P naught minus rho g h naught will be equal to zero. Means the pressure at the top becomes zero. Means the water is not pushing your thumb anymore. Your thumb is also not effectively exerting any force on the water anymore. Okay, let me show you that situation also. Just a moment. Let's say when the tube is pulled out by this much height. Let's call this height as h naught. The pressure at the top becomes zero. That is P naught minus rho g h naught becomes zero. If pressure at the top becomes zero, you visualize the liquid that is inside the tube now. what forces act on the liquid which is inside the tube above the outer water surface? What does that mean? I'm talking about this part of the liquid. What forces act on it? Its weight will be acting. How do you express its weight? Density into volume. Volume is area of cross section multiplied with the height, multiplied with g. Its weight will be acting. Okay? And the pressure at the lower surface here is P naught. If the pressure is P naught, then at this cross section, there will be a force acting in the upward direction, which is P naught into dA. So that force will be acting upward. P naught dA. Fine. And see, we have taken it to a height where P naught minus rho g H naught is equal to 0. Means P naught balances rho g H naught. That means these two forces balance. That means the net force on the liquid now is 0. Which liquid? On the liquid inside the tube, which is above the liquid surface outside the tube. The net force on that part becomes 0. Okay. What will happen if you lift the tube any higher than this? If you lift the tube higher than this, you'll have a tendency to uh, what do you say? You'll have a tendency to carry more liquid inside that space, inside that tube. So imagine something like this. Imagine taking it even higher. Now at the height h naught, its weight is exactly balanced by force due to atmospheric pressure. If you take it any higher, then at this level from below, there will be force due to atmospheric pressure, but now the weight will be heavier because the height is greater than h naught. Okay. And because the weight is greater than the force exerted by atmospheric pressure, you will see the liquid level inside the tube coming down. Okay. It will settle at h naught itself. It cannot go higher than that. It cannot increase greater than that. So you will see some empty space here, and in that empty space, what will be there? Vacuum will be there. Okay. Once the weight of the liquid column gets balanced by force due to atmospheric pressure from below, the liquid column cannot increase any longer. Okay, the length of the liquid column cannot increase any longer. Okay, that is the height to which it gets restricted. After that, you will see a vacuum forming. Is this clear to all of you? Did you understand how all this happens as the tube is lifted out of the container? If you have any questions, you can ask. Okay, let me quickly explain this once again. As the tube is sealed at the top and raised above the water surface, okay, surrounding water surface, the pressure at this level outside and inside the tube will be P naught. Always, it has to be like that. We are gently raising it up. You can consider it as a static fluid itself. Very slowly, we are lifting it up. Okay. So flow of the fluid and all can be ignored. You can assume it to be almost static. So the pressure at that level outside the tube and also inside the tube will always be atmospheric pressure. Fine. If the pressure at that level is atmospheric pressure, pressure anywhere above that should be less than atmospheric pressure in the liquid. So the pressure at the top where you have closed the tube will be P naught minus rho g h. It will be less than atmospheric pressure. So if you consider this part of the liquid, what forces will be acting on it? Its weight will be acting on it, and force due to atmospheric pressure will be acting on it. Initially, when you lift the tube out only by a small height, the weight will be small, but the force due to atmospheric pressure will be significant. Okay, which is in the upward direction. So basically the liquid will be pressing on your thumb by which you have sealed, with which you have sealed the top of the tube. Okay, so that is what I mentioned here. P naught minus rho g h will be positive. There will be positive pressure at the top, means you can feel the liquid pushing against your finger. Okay, as you continue lifting the tube out of water, out of the liquid, what happens is at one height, okay, the weight of liquid inside the tube gets balanced by force due to atmospheric pressure. Okay, when I say weight of liquid inside the tube, I only mean weight of liquid which is outside the remaining liquid, this part. That weight becomes equal to force due to atmospheric pressure. Once those two forces balance, the liquid will no longer be pressing your thumb. Okay, you can feel it. And I'm sure some of you might have tried this with straws also while drinking water from a straw. You put the straw into water, you close the upper end of the straw, you take it out. You'll see some water still hanging inside the straw. The moment you release the thumb, water will drain out of the straw. Okay, so this is the mechanism there basically. Now, if you lift the tube to a height greater than h naught, now what will happen? If the height actually becomes greater than h naught, weight will be more than force due to atmospheric pressure. Okay, weight of liquid above the surrounding liquid becomes more than atmospheric pressure, force due to atmospheric pressure. Then it will have to go down. If weight dominates, the liquid will have to go down. As it goes down, the weight outside will decrease. The weight of liquid outside will decrease. It will fall down to h naught again and settle there. Okay, beyond that, you lift the tube to any height, you will only see empty space at the top, and that empty space is basically vacuum. There's nothing present there. There's no way air can enter in. Okay. Why? See, there's no reason why air should enter in. No. Here the pressure is P naught. Okay. Inside the tube also pressure is P naught. Why should air go from here to here? How can air go into the tube? That's not possible. Only when you take the tube completely out of water, out of liquid, it's possible for air to enter in. But we are not considering that situation. We are considering the tube is long enough. Okay. So air will not enter into the tube. You will see empty space there, which is vacuum at the top. Okay. So at what height does liquid settle finally if the tube is long enough? It settles at a height. Okay. The liquid in the tube settles at height h naught such that atmospheric pressure P naught is equal to rho g h naught. It will always settle like this. And remember, we are considering the case where the container is not accelerated. If container is accelerated, then the pressure variation will be different. You won't write P naught minus rho g h naught. You will write P naught minus rho g plus a into h naught or g minus a into h naught. Okay, then the equations will change. Okay, the height will change. Anyway, in a non-accelerated container, the liquid settles to such a height that P naught becomes equal to rho g h naught. Now, if you know the density of the liquid and you know acceleration due to gravity anyway, and if you can measure this height, you can tell how much is the atmospheric pressure at that place. This is what a barometer does. Okay, so this apparatus is actually a barometer, just a beaker consisting of liquid and a tube which is long enough. Okay, usually the liquid will be mercury and the tube should be more than 1 meter long, 1 meter or more than that. Mercury settles at a height 76 centimeters, which is comfortably less than 1 meter. Okay, so you keep lifting the mercury tube out. Okay, once the tube is completely filled with mercury, you keep lifting it out. I told you, mercury should not touch your skin directly, so you must be wearing protective gear or maybe seal the tube with something else. Okay, ensure the tube is completely filled with mercury and start lifting it up. You will see that once you lift it to a height of 76 centimeters, mercury will not rise higher anymore. It will settle at that level, 76 centimeters. If it's some other liquid, it will settle at some other height, depending on its density. You can calculate that height also. Okay. So the height where the liquid settles is P naught by rho g. Or if you know the height at which the liquid is settling, from rho g h naught, you can tell what is the atmospheric pressure there. So that is what a barometer does. Fine. So basically it consists of beaker which is exposed to atmosphere. The beaker must be exposed to atmosphere because it is important that the pressure at this level is equal to atmospheric pressure. Okay, so the beaker must be exposed to atmosphere. Then the pressure at the same level inside the tube also will be atmospheric pressure itself. Based on the height of the liquid column inside the tube, you can tell what is the atmosphere or how much is the atmospheric pressure. That is how a barometer works. Is this clear to all of you? Any doubts in this? So there's a beaker filled with some liquid, usually mercury. You insert a tube, ensure the tube is completely filled with the liquid, seal the top end of the tube and start pulling it out. Based on the height at which liquid settles, you can tell how much is the atmospheric pressure. Okay, the equation is P naught is equal to rho g H naught. So let me write the condition here. When container is not accelerated. Okay. Let's solve one problem based on this. A basic situation, you can deal with it. Let me write the question, just a moment. Right. Now consider this question. Suppose a barometer is placed in an elevator. The pressure in the elevator is known to be 1 atmosphere, okay? Atmospheric pressure only. If the elevator accelerates upward, okay? See, elevator is filled with gas. Apart from the barometer, the rest of the elevator is filled with gas, air. Whether you accelerate air upward or downward, the air is a gas. Pressure in a gas is due to motion, random motion of gas molecules, not due to gravity. Okay. So acceleration of the elevator is not going to change the pressure inside it. Okay. So the pressure continues to remain 1 atmosphere. These things they won't explain to you in the question. You should understand this from your own logic. Okay. Air is a gas. Its pressure won't change based on whether container is accelerated or not. Okay. So even when the elevator is accelerated, the pressure inside it will still be 1 atmosphere. Now it is told to you that the elevator accelerates upward with an acceleration equal to g by 2, half the acceleration due to gravity. Okay, that's a significantly high acceleration. Calculate the height at which the mercury column in the barometer settles. Okay, in a non-accelerated container, you know the liquid settles at 76 centimeters. Okay, that need not be told to you. Usually, the mercury level will settle at 76 centimeters. But if it is placed in an elevator accelerated upward, at what level does it settle? Okay. Think about it and solve all of you. I'll give you all 3 minutes. Aishwarya, tell me, suppose the container was not accelerated, you know it would have settled. The mercury column would have settled at 76 centimeters outside the remaining liquid. How do we get that height in a non-accelerated liquid? At what height the liquid settles, which equation helps us calculate?
So P naught by rho g.
P naught is equal to rho g H naught. So if you know the pressure there and the density of liquid and acceleration due to gravity, you can tell the height at which it settles. Fine. Now the pressure is given to you inside this elevator, but the elevator is accelerated upward. Aishwarya, you tell me, when elevator is accelerated upward, what change should we make in this equation? If the elevator is accelerated upward, what change should we make in this equation?
Sir, it will be g plus a.
That's all. Correct. So when it is accelerated upward, the pressure, whatever is the pressure of the surroundings, okay, which is what is given to you as atmospheric pressure, becomes rho g plus a multiplied with h dash, new height. That's all. So the new height becomes P naught by rho into g plus a. Now a is given as g by 2 in this question. G plus g by 2 is 3g by 2. So P naught by rho into 3g by 2. 2 will go to the numerator. So 2/3 of P naught by rho g. Now what is P naught by rho g? The usual height at which the mercury level would have settled. Okay. The usual height at which the mercury settles is 76 centimeters. Now it will be 2/3 of that. That calculation you should be able to do. Okay. So basically what happens here is if the container is accelerated upward along with the tube is also accelerated. Everything is inside the elevator now. Okay. So if all these things are accelerated upward, you will need to include a pseudo force in the downward direction. The liquid feels heavier. Okay. So since the liquid feels heavier, a smaller height itself will be balanced by force due to atmospheric pressure. That is the logic. Okay, we got the answer as 2/3 of the normal height. Okay, 2/3 means smaller only, no? So because the mercury feels a lot heavier now due to the upward acceleration, apparent weight will be more than actual weight. The mercury feels heavier. As a result, a smaller height of mercury column will be balanced by force due to atmospheric pressure. And that height is 2/3 of 76 centimeters. Based on the acceleration, you can tell what height. You can solve this question when the barometer is accelerated downward also, or the elevator is accelerated downward also. In that case, it becomes G minus A. Fine. Okay, we'll stop it here for today. Let's quickly revise what all we discussed. We first discussed this situation where if you make a hole in a container, will liquid flow out or air flow in? And you all know that liquid flows out. We discussed why that happens. And in this case, if the container is open at the top, you will see liquid flowing out continuously. Air will not go in at all. Okay, liquid will continuously flow out till the level of liquid inside comes down to this. Till then, you will see the liquid flowing out. Air will not go in at all. Why? Because the pressure at the top is always atmospheric pressure. Then the pressure at this level where the hole is made will always be more than atmospheric pressure. So liquid is at a pressure more than atmospheric pressure, which is air pressure outside. So liquid will keep going out. Okay. Then we discuss the case of this water can. Okay. We know that as we draw water from this can, okay, at regular intervals, bubbles will enter inside the can. Why does air have to enter inside? That case we discussed. And after that, we started talking about how pressure can be expressed in terms of length of a liquid column. Okay. You just have to find out what vertical length of a liquid column creates a pressure of 1 atmosphere. Okay. So rho GH is equal to P naught. Based on that, you can tell. So usually approximately 76 centimeter long mercury column creates a pressure equal to 1 atmosphere. Okay, that is why we express atmospheric pressure in terms of length of a mercury column. Okay, that's the logic behind it. You can express it in terms of length of any liquid column, even water. In case of water, it will have to be 10 meters long. It all depends on density. Okay, then a barometer is an instrument which makes use of this property. And we discussed how a barometer works. There'll be a beaker consisting the liquid, usually mercury. You insert a tube which is open at both ends completely into the beaker. So the tube will be completely filled with liquid. Then you seal the top of the tube and start lifting it out, pulling it out. You will see that the liquid settles at a particular height. After that, even if you pull the tube further out, the liquid level will not rise inside it. Okay. So based on the height at which the liquid level settles, you can tell what is the pressure outside. You can tell how much is P naught. Okay, the equation is P naught is equal to rho g H naught. H naught is P naught by rho g. But this is valid only when the container is not accelerated. If it is accelerated upward, we solve the problem. In place of g, you write g plus a and get the height. If it is accelerated downwards, in place of g, you write g minus a and get the height. Okay, that is how a barometer works. Fine.